Okay, so I wanted to take a look at the inverse trig functions, and um, you really just need to be able to do the derivatives of the inverse trig functions. But I wanted to give you just a little background on inverse trig functions before we do that. Okay, so the y equals arc sine x, that notation is the same as, let me get a color here, is the same as sine inverse. And be careful, don't be thinking that sine inverse of x means 1 over sine x. That's completely incorrect. That notation means the inverse of sine, and arc sine is another way to say that, and it's less likely to cause you to think 1 over sine, because that's not true at all. So what inverse functions do in general is they take the ordered pairs on the original function and they interchange the x and the y's. All the ordered pairs would have the x's and the y's interchanged. So like with sine, if you're doing sine, you do sine of, you should think of it like maybe the sine of an angle, and then you get some value as your output. Okay. So the sine of some angle gives you your value. With the inverse sine function, with arc sine, what happens is your input is an angle, and then the value of the arc sine of that, oh wait, I just said that backwards. Sorry. The input to arc sine is a value, and then the output from it would be the angle. Okay. So your answer to an arc sine question like find arc sine of 1/2 would turn out to be some angle. But then one of the tricky parts of this is sine, cosine, tangent, all of the trig functions are periodic. They're not one-to-one. So if you tried to do the inverse of them, the inverse would not be a function unless you restrict your domain, the domain of the sine function, cosine or tangent functions, so that it would be one-to-one. So you'll have these special conditions here, because like sine is going to be a function that looks something like this, right? Keeps going forever, both directions, fluctuating between 1 and -1. All right. So if let me change this one to blue. Okay. So if we were trying to find the answer to the question, arc sine of 1/2, we're really trying to answer the question, what is the angle whose sine would be 1/2? And there'd be a lot of answers. Look at all these values here that would have wound up being angles that have a sine of 1/2. So if you want your input to have only one output, if you want the answer to the question to be one thing, then you have to restrict the sine function in some way. And the customary way we do that is to cut off this piece from -π/2 to here, which would be π/2. Okay, so from -π/2 to π/2. We take that piece, which is now 1-to-1. So then there's only one angle that would have a sine of 1/2, and that angle would be π/6. So your answer to this question would be π/6. Think about it on a unit circle. Okay, π/2, -π/2. And you're supposed to restrict your answer to be an angle between those two over here. And so it's just this angle right here that would have a sine value of 1/2. And that angle right there, this angle right there would be π/6. Okay. So just a little bit of background. So I wanted you to see this idea just with sine for a minute. And then we'll do just a little bit more on that concept. Look at the chart that I gave you below. Okay. So the functions where we have over here are the inverse trig functions. And then what they've done is they've shared with you that reminder that for sine, which looks like this, we're going to cut off the section of sine from -π/2 to π/2. Okay, so think about that like we did earlier. Let me draw that little picture for you. So we're talking about reporting an angle that is somewhere between negative pi over 2 and pi over 2. Okay. All right, with cosine looks a lot like sine. Okay, I'm going to move it over a little bit. It starts at 1 and does that same thing. Okay. All right, and then what we're going to do there is we're going to snip the cosine function from 0 to pi so that we have a one-to-one piece. So when we do the inverse, it would be a function. And on the unit circle, that means what we're going to be using is, or looking at, is this part from 0 to pi. Okay, that's what that says. All right, and then with the trig function, the tangent function, it does this, doesn't it? It looks like that, and then it repeats that shape, okay, multiple times. And there, what we're going to do is take just one piece of it, which would be 1-to-1, the most natural piece right there around the origin. And it's kind of like sine on the unit circle because it has to do with negative pi over 2 to pi over 2. So this side of the unit circle, it's just you can't include the endpoints on that one. They don't have the or equal to on it because that's where the asymptotes would have been. And I won't draw all the rest of them. Okay. All right. Now, the main thing, you don't really have to know a whole lot about inverse trig functions and how to work with them, but you do need to be able to get their derivatives, okay? And occasionally you might be asked to find the value so that you can get slope or something like that, but really it's more just being able to do the derivatives. So we're getting ready to do that. Let's take a look at the derivative rules. You need to know these, so memorize these. And I'll show you how to derive them. And then that might help you memorize them. Also, look at the pattern. It's the same thing that happened before. Do you see how you have a negative on the ones on the right, but they're exactly the same as the related ones on the left? Okay, so here's your sine, tangent, secant, arcsine, arctan, arcsecant. And then when you look at the cofunction over here, so arccosine, arccotangent, arccosecant, you have to have the negative on everything. And then I'm going to go ahead and derive a couple of these so you see why you get what you get. I can derive all of them, but I'll do just 2 or 3 of them. And then we'll do another video where we're working problems. Okay. So just so you see why the derivative turns out that way, let's take y equals arc sine x. Okay. All right. So y equals arc sine x means that the sine of y should equal just x. So if I did like sine on both sides, I would wind up with sine y has to be x. All right, so now I want you to think about your right triangles. All right, and sine of something, sine of y. Y is like the angle, so think about the y being here. And the sine ratio turned out to be x, which is like x over 1. So take your right triangle and think about that. Sine is opposite over hypotenuse. So that means on my right triangle, I would want to put the x across from the angle y, and I would use 1 as the hypotenuse. Well, then I could figure this out using the Pythagorean theorem, right? Because I know that whatever that is, squared, so let me call it a. So let's say that's a. I know that a squared plus x squared would have to equal 1. So a squared would equal 1 minus x squared. And if I square root both sides, I get the square root of 1 minus x squared. Okay? So think about that. So this side right here now, I know this side is the square root of 1 minus, let me actually erase what I had before and just put 1 minus x squared right there. Okay? So this is the square root of 1 minus x squared. All right, so now coming back over to where I had sine y equaling x. All right here. So I had sine y was equal to x. Now, I want to do the derivative of both sides. Now, this is a little bit, I'm using a little bit of something that we'll actually talk about later, but I think you can follow it okay. So y, remember, is a function of x, right? So when I do the derivative of sine y, I'll get cosine y, but I have to do the derivative of that inside piece. So I'm going to have to multiply that by y prime, because y is a function of x. Okay, and then the derivative of x would be 1. All right, and we're trying to come up with a formula for the derivative. So I'm going to get this on a side by itself by dividing by cosine y. And I wind up with y prime equaling 1 over cosine y. All right, so now I'm going to go back up to this right triangle now and think about that. So 1 over cosine y, cosine y. Cosine is adjacent over hypotenuse. So the adjacent side would be 1 minus square root of 1 minus x squared over the hypotenuse, which would be 1. So that would just be 1 over the square root of 1 minus x squared. Okay? So that was when I was looking at how to get, all I was really proving was the formula for the derivative of y equals arc sine x. So here it is. Okay. But if instead of just x right here, if we had y equals arc sine of some function of x, right, like a u that could be something like 3x plus 1, then we'd have to modify that just slightly. We would still do this, do the square root of 1 minus our input squared, but we'd have to multiply it by the derivative of the inside function. And then they write that with the u prime on top is where that comes from. Okay? So that's proving arc sine and what it turns out to be. We could go through a similar thing to prove cosine and tangent and secant and all the rest of those. So let me do one more. Let's try to do maybe the derivative of, maybe we'll do, you want to do the derivative, I could do tangent to see why that turns out. Maybe I'll do the derivative of, or find out why secant turns out the way it does. The others I think you could almost do on your own. So let's say we want to prove why the formula for arc, the derivative of arc secant turns out the way it does. Okay, so for that one, I would think, okay, well, I want to interpret that, change that in my mind into one of the normal trig functions. I'm trying to get some more space in here real quick. I can get it to do that. Nope. Okay. So if I have y equals arc secant x, then it should be true that the secant of y would equal x. Okay. And then if I did the derivative, well, let me go ahead and draw my triangle. So then if I thought about my triangle on that, okay, y is my angle. Remember, secant is related to cosine. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So remember, this one is the hypotenuse over the adjacent. It's the reciprocal of what you would have gotten for cosine. So that would mean I'd want the hypotenuse to be x, and I'd want the adjacent side to be 1. Still could use my Pythagorean theorem to find that missing side like I did on the other problem. And I'd wind up with a squared, and that would be 1 squared, but 1 squared is 1. I'd wind up with a squared equaling x squared minus 1. So a would equal the square root of x squared minus 1. Okay, so that's right here. That equals the square root of x squared minus 1. Okay. All right, so now I'm going to go through, I'm trying to get the derivative in there. So I'm going to do the derivative with respect to x. So the derivative of secant would be secant tangent, so secant y, tangent y, but then this is a function of x, so I need to do the derivative of y. And then I do the derivative of x on the other side, which would be 1. So I'm using a technique that I really didn't tell you about called implicit differentiation, but I think you can follow along enough to see where these formulas come from. Okay. Now what I'm going to do is I'm going to wind up getting y prime on a side by itself by dividing by secant y tangent y. All right. Then I'm going to look at my right triangle again, and I'm going to replace secant y with what it's equal to. So I know it's equal to x. And then I'm going to replace tangent y. Tangent, so secant we know is hypotenuse over adjacent. And then tangent is opposite over adjacent. So looking at my triangle, the opposite side would be square root of x squared minus 1. Adjacent would be 1. The secant would be x over 1. So I wind up with 1 over x, square root of x squared minus 1. Now we do have a little bit of an issue when we're doing when you look at the formula there. We actually need this x to wind up being put in absolute value symbols. The secant should wind up having a positive slope. And so I could get into trouble if I were looking at an area of the graph where x were negative. So it does have the absolute value on that. So you had to think about that needing absolute value on it. Okay. All right. But if you'll allow me that, then you can see that if I change the function to be more general and I do arc secant of u, which is some function, something other than just an x, then we'll just modify that formula a little bit and we'll put a u instead of an x in there. Oops, a u instead of an x. And then we'll also wind up having to take, since it's now a function of x in there, having to take the derivative of that. So that's where that formula comes from. Okay. All right, so I just wanted to derive a couple of them, also go over the gist of what an inverse trig function would be, and then in the next video, I'll work these problems.